Right now, at this very moment, you're trapped. We all are. Not by walls or gravity, but by something far more fundamental, a cosmic speed limit woven into the very fabric of reality itself. The speed of light, roughly 186,000 miles per second, represents an absolute barrier that nothing with mass can cross. This limitation has sentenced humanity to crawl through a universe so vast that our fastest spacecraft would take over 70,000 years just to reach the nearest star beyond our Sun. To truly grasp the enormity of this constraint, consider what it means in practical terms. The Andromeda Galaxy, our nearest major galactic neighbour, lies 2.5 million light-years away. Even travelling at the speed of light, an impossibility for any object with mass, you would need 2.5 million years to reach it. Your journey would span a duration longer than the entire existence of our species. The stars you see in the night sky, those pinpricks of light that have inspired poets and philosophers for millennia, are so distant that their light has taken years, decades, or centuries to reach your eyes. You're seeing them not as they are, but as they were. The universe we observe is a museum of the past, and we are isolated within it by the tyranny of distance and the limitations of velocity. For generations, physicists dismissed faster-than-light travel as pure fantasy, relegated to the pages of science fiction novels and the dreams of starry-eyed visionaries. The mathematics were clear, the experimental evidence overwhelming. Albert Einstein's special theory of relativity, published in 1905, demonstrated with elegant precision why the speed of light represents an absolute cosmic speed limit. The theory has been tested thousands of times in particle accelerators, astronomical observations, GPS satellites, and countless other experiments. Every test confirms its predictions. The speed of light is not just fast, it is the maximum speed at which causality itself can propagate through the universe. To exceed it would require infinite energy and would create paradoxes that would shatter the logical consistency of physical law. Or so we thought. But something remarkable has happened in the last year. In 2024, a team of international scientists published findings that fundamentally changed the conversation about warp drives. For the first time in 3 decades of research, they demonstrated a method that doesn't require the impossible, exotic negative energy that may not exist anywhere in our universe. Instead, they've shown how ordinary matter, manipulated in extraordinary ways, could bend spacetime itself into a bubble capable of transporting objects at speeds that effectively bypass light's iron grip on cosmic travel. This breakthrough represents more than just an incremental advance in theoretical physics. It represents a paradigm shift in our understanding of what might be possible. The research team didn't just refine existing concepts, they discovered an entirely new approach that sidesteps the fundamental obstacle that had blocked progress for 3 decades. They found a loophole in the laws of physics, not by breaking those laws, but by understanding them more deeply than anyone had before. This isn't science fiction anymore, this is physics. Real physics, published in peer-reviewed journals scrutinized by experts worldwide. The equations work, the simulations confirm it, the mathematical framework is sound. We may not be able to build a warp drive today, or even in our lifetimes, but we now know with reasonable confidence that it can be built eventually. That knowledge changes everything. It transforms the stars from unreachable lights in the sky to potential destinations. It converts the galaxy from an abstract concept into a territory we might someday explore. It offers humanity a future that extends beyond our tiny pale blue dot, into the cosmic ocean that has called to us since we first looked up and wondered what lies beyond. Prepare yourselves. We're about to journey through the greatest transportation revolution in human history. We'll explore the physics that both constrains and liberates us. We'll examine the breakthrough that makes warp drives theoretically possible. We'll investigate the engineering challenges that stand between concept and reality. We'll consider what it would mean for humanity to become an interstellar species. And we'll confront the question that has haunted dreamers and scientists alike for generations: can we travel faster than light? The answer, as you're about to discover, is more nuanced and more exciting than a simple yes or no. The universe has a speed limit, and it's frustratingly slow when you consider the distances involved in space travel. Light moves at approximately 299,792,458 meters per second in a vacuum. That sounds incredibly fast until you realize that at this speed, it still takes light over 4 years to reach Proxima Centauri, our nearest stellar neighbour. To traverse our own Milky Way galaxy from one end to the other would consume 100,000 years, even for a photon racing at maximum cosmic velocity. The galaxy next door, Andromeda, lies so far away that light from it takes 2.5 million years to reach us. When you look at Andromeda in the night sky, you're seeing it as it appeared 2.5 million years ago, long before modern humans existed on Earth. For anything with mass, a spaceship, a human body, even a single atom, the situation is far worse. As Einstein revealed in his special theory of relativity, published in 1905, the faster an object moves, the more its mass effectively increases from the perspective of a stationary observer. This isn't just a theoretical curiosity or mathematical abstraction. It's a measured, verified property of reality that governs how particles behave in accelerators and how GPS satellites must correct their timekeeping. Approaching light speed, an object's relativistic mass grows toward infinity, requiring infinite energy to accelerate further. This mathematical wall doesn't just make faster-than-light travel difficult or expensive, it makes it theoretically impossible within the framework of special relativity. The equations are clear, verified countless times through experiment. Nothing with mass can reach, let alone exceed, the speed of light in normal spacetime. The deeper reason for this cosmic speed limit lies in the structure of spacetime itself. Before Einstein, space and time were considered separate entities, an absolute space through which objects moved, and an absolute time that flowed uniformly everywhere. Einstein's breakthrough was recognizing that space and time are intimately connected, forming a four-dimensional continuum called spacetime. Events that seem simultaneous to one observer occur at different times for another observer moving at a different velocity. Distances contract, time dilates, and mass increases with velocity. These aren't illusions or measurement errors. They're fundamental properties of the universe we inhabit. The speed of light emerges from this framework not as an arbitrary limit, but as a structural feature of spacetime itself. It represents the maximum speed at which cause and effect can propagate. It's the speed at which massless particles must travel, and the speed that massive particles asymptotically approach, but can never reach. Understanding why this limit exists requires examining what happens as objects approach light speed. Imagine accelerating a spacecraft using conventional propulsion. At low velocities, doubling your thrust roughly doubles your acceleration. But as you approach significant fractions of light speed, something strange happens. The same amount of thrust produces less and less acceleration. The spacecraft's inertia increases, making it harder to accelerate further. From the spacecraft's perspective, everything seems normal. Clocks tick at their usual rate. Masses feel the same. But from an external observer's viewpoint, the spacecraft's time slows down, its length contracts in the direction of motion, and its mass increases. These relativistic effects become extreme as velocity approaches light speed. At 90% of light speed, time aboard the spacecraft runs at about 44% the rate of stationary clocks. At 99%, it's down to 14%. At 99.9%, time runs at just 4.5% of normal. As you get arbitrarily close to light speed, time dilation approaches infinity. You could never actually reach light speed with any finite amount of energy. This creates what scientists call the interstellar travel problem, and it's more severe than most people realize. Our fastest human-made object, the Voyager 1 spacecraft, travels at roughly 38,000 miles per hour, a breathtaking velocity by terrestrial standards. It's moving fast enough to circumnavigate Earth in about 40 minutes, yet at this pace, Voyager would need approximately 75,000 years to reach Proxima Centauri if it were heading in that direction, which it isn't. Even travelling at 10% the speed of light, a velocity we have absolutely no idea how to achieve with current technology, the journey would still consume over 40 years. A human crew would age throughout the voyage. Generations would pass. The travellers who arrived would bear little resemblance to those who departed Earth. For practical interstellar exploration and colonization, humanity needs something dramatically better. We need to travel not just fast, but impossibly fast by current standards. We need to break the cosmic speed limit without actually breaking it, to move faster than light while respecting the fundamental laws of physics that forbid such movement. This apparent paradox contains within it the seed of a solution. The key insight that makes faster-than-light travel theoretically possible comes from understanding exactly what Einstein's relativity prohibits. The speed limit applies to objects moving through spacetime. It says nothing whatsoever about the movement of spacetime itself. This is a crucial distinction that opens the door to possibilities Einstein himself might not have imagined. Space can expand, contract, warp, and flow at any rate, including rates far exceeding the speed of light. There's no cosmic speed limit on spacetime's own dynamics. In fact, space itself expanded faster than light during the universe's inflationary period immediately after the Big Bang. Distant galaxies currently recede from us at superluminal speeds due to cosmic expansion, not because they're moving through space faster than light, but because the space between us and them is expanding at that rate. The fabric of reality has no speed limit. Only objects travelling through that fabric do. If we could manipulate space-time itself, we might achieve effective faster-than-light travel without technically moving faster than light, relative to the space immediately around us. We would contract space in front of our spacecraft and expand it behind, creating a moving bubble of distorted geometry that carries us along like a surfer riding a wave. From the perspective of someone inside the bubble, they wouldn't be moving at all relative to the local space-time. Their local physics would remain completely normal, clocks tick at standard rates, light moves at its usual speed, masses stay constant. But the bubble itself surges forward as space contracts ahead and expands behind, propelling the spacecraft forward at speeds that could exceed light speed when measured by distant observers. This brilliant loophole in the laws of physics has captivated theoretical physicists for decades. The question has never been whether the laws of physics permit this in principle. They clearly do, as general relativity explicitly allows for such space-time geometries. The question has always been whether we could actually build such a device, whether we could generate and control the necessary space-time curvature, whether we could do it without requiring impossible resources or violating other physical principles. For 30 years, the answer appeared to be no. The requirements seemed insurmountable. But in 2024, that answer changed. In 1994, a young Mexican physicist named Miguel Alcubierre Moya sat in his dormitory at the University of Cardiff in Wales, pondering a question that millions of Star Trek fans had asked, but few scientists seriously considered. Could the Enterprise's warp drive actually work? Alcubierre was pursuing a PhD in numerical relativity, studying the complex mathematics that describe how matter and energy curve spacetime according to Einstein's general theory of relativity. He spent his Friday nights watching Star Trek, The Next Generation with friends, and one evening, the fictional faster-than-light propulsion system captured his imagination in a new way. Instead of dismissing it as impossible fantasy, he asked himself a different question. What would the mathematics of such a device actually look like? Over the following weeks and months, Alcubierre worked through the problem methodically, applying the field equations of general relativity to the concept of faster-than-light travel. He wasn't trying to violate relativity, he understood that was impossible. Instead, he searched for a space-time geometry that would allow a spacecraft to travel faster than light while remaining within the framework of Einstein's equations. The question wasn't whether you could move through space faster than light, which relativity forbids. The question was whether you could arrange spacetime itself in such a way that space moves faster than light, carrying you along with it. This subtle but crucial distinction opened up entirely new possibilities. What emerged from his calculations would become one of the most influential papers in theoretical physics, a work that would inspire thousands of subsequent research papers and fundamentally change how scientists think about interstellar travel. Published in May 1994 in the journal Classical and Quantum Gravity, Alcubierre's paper described a space-time geometry that could, in principle, allow faster-than-light travel while remaining consistent with Einstein's general relativity. The paper was titled The Warp Drive: Hyperfast Travel Within General Relativity, and its central insight was both elegant and revolutionary. Alcubierre showed that you could construct a metric, a mathematical description of space-time geometry, where a bubble of flat space-time exists within a region of highly curved space-time. Inside this bubble, physics operates normally. Clocks tick at their usual rate. Light travels at its standard velocity. Objects experience no unusual forces, but the bubble itself moves through space, propelled by the asymmetric curvature of spacetime around it. The Alcubierre drive works by creating what physicists call a warp bubble through a specific pattern of spacetime curvature. Imagine spacetime as an infinitely flexible rubber sheet that can be stretched, compressed, and deformed in complex ways. Under normal circumstances, objects must travel across this sheet, limited by how fast they can move through the material. The speed of light represents the maximum velocity for such conventional travel. But the Alcubierre metric does something fundamentally different. It contracts spacetime in front of the spacecraft, bringing distant points closer together like bunching up the rubber sheet. Simultaneously, it expands spacetime behind the craft, pushing the starting point further away like stretching the sheet. The spacecraft itself sits inside a region of flat, undistorted spacetime, the warp bubble. This bubble surges forward as space contracts ahead and expands behind, carrying the ship, along without the ship itself moving through space in the traditional sense. The mathematics revealed something extraordinary. From the perspective of an observer inside the bubble, local physics operates completely normally. You could float freely in the cabin, experiencing no acceleration forces whatsoever. Light traveling across the cabin moves at its usual speed. Time flows at its ordinary rate. You might look out a window, though what you'd see would be wildly distorted by the curved spacetime around the bubble. But inside, everything feels perfectly normal. Yet the bubble itself travels through space, and it can travel at any velocity, even many times the speed of light. This works because it's not the ship moving through space, but rather the geometry of spacetime itself that's arranged to carry the bubble forward. In general relativity, there's no restriction on how fast spacetime can flow or how quickly its geometry can change. The speed limit applies only to objects moving through spacetime, not to spacetime's own dynamics. Alcubierre calculated exactly what spacetime curvature pattern would produce this effect. The metric he derived showed that you need strong positive curvature behind the ship and strong negative curvature in front of it. The region of positive curvature expands space exponentially, while the region of negative curvature contracts it. The gradient between these regions, the boundary where curvature transitions from positive to negative, propels the bubble forward. The steeper the gradient, the faster the bubble moves. In principle, there's no upper limit to the velocity. You could traverse the galaxy in days, travel between galactic clusters in weeks, cross the observable universe in months. The constraints imposed by special relativity's speed limits simply don't apply because you're not moving through space faster than light. You're riding a wave of space-time curvature that carries you forward. The mathematical elegance of Alcubierre's solution captivated the scientific community immediately. Here was a rigorous demonstration that the laws of physics didn't absolutely forbid faster than light travel. They merely constrained how it could be achieved. The warp drive wasn't violating relativity. It was using relativity's own mathematical framework to create a loophole through which faster-than-light travel became possible. The paper was carefully reviewed and published in a leading physics journal. The mathematics checked out. The solution satisfied Einstein's field equations. Everything appeared to work, at least on paper. Physicists worldwide began examining Alcubierre's metric, checking his calculations, exploring its properties, and asking whether it could ever be built in reality. But enthusiasm quickly tempered when researchers examined what the Alcubierre drive would actually require to function. The calculations revealed a devastating problem that seemed to doom the concept from the start. To create the necessary space-time curvature, the warp drive needed exotic matter with negative energy density. This isn't antimatter, which despite having opposite charge still possesses positive energy and creates normal gravitational attraction. It's not dark matter, which also has positive gravitational effects. This is truly exotic matter with properties unlike anything observed in nature, matter that would create repulsive gravitational effects, pushing spacetime outward rather than pulling it inward, matter that would have effective negative mass, violating every intuition we have about how mass and energy behave. Negative energy isn't merely hard to find or expensive to produce. Most physicists believe it may not exist at all in usable macroscopic quantities, and there are profound theoretical reasons to suspect it cannot exist. Quantum field theory does predict that certain quantum effects can produce tiny amounts of negative energy density at microscopic scales under very specific conditions. The Casimir effect represents the best-known example. When two uncharged metal plates are placed extremely close together in a vacuum, separated by less than a micrometer, quantum fluctuations of the electromagnetic field create different radiation pressures on the inner and outer faces of the plates. The plates experience a small attractive force because the space between them contains slightly less electromagnetic energy than the space outside. This creates a tiny region of negative energy density between the plates, measurable in careful experiments. But the Casimir effect generates infinitesimal amounts of negative energy, confined to gaps smaller than 1,000th of a millimeter. Scaling this up to create a warp bubble around a spacecraft would require negative energy equivalent to the mass energy of multiple Jupiter-mass planets, all concentrated in a shell around the ship and maintained stably for the duration of the journey. Even if we could somehow generate such quantities, and we have no idea how, we'd need to stabilize this exotic matter, prevent it from dispersing or annihilating, and shape it into the precise geometric configuration required by Alcubierre's metric. The engineering challenges seemed insurmountable. The energy requirements were astronomical even by cosmic standards, dwarfing anything humanity could conceivably produce. Alcubierre's original calculations suggested that creating a warp bubble just a few meters in diameter would require an amount of exotic negative energy comparable to the total mass energy of the Sun. Later refinements by NASA physicist Harold White and others reduced these requirements somewhat by optimizing the bubble's shape, but the numbers remained absurdly large. We're talking about energy densities and exotic matter distributions that would make building a Death Star look simple by comparison. For 3 decades, the Alcubierre drive remained a beautiful mathematical solution to an unsolvable engineering problem. It showed that faster-than-light travel wasn't prohibited by the laws of physics, but it might as well have been. The requirements were so extreme, the materials so exotic, that most researchers viewed warp drives as permanently confined to the realm of theory. Some physicists continued tinkering with the equations, searching for ways to reduce the energy requirements or eliminate the need for exotic matter. Progress came in tiny increments, but the fundamental barrier remained. To create a warp bubble using Alcubierre's original framework, you needed something that probably didn't exist. That was the state of warp drive research when 2024 began. Then everything changed. In May 2024, Applied Physics, an international think tank of over 30 scientists and engineers, published a groundbreaking study in the prestigious journal Classical and Quantum Gravity. The paper, led by Dr. Jared Fuchs, with contributions from researchers at institutions including the University of Alabama in Huntsville, presented something the scientific community had been seeking for 30 years, a warp drive design that doesn't require exotic negative energy. This wasn't an incremental improvement, it was a paradigm shift. The team introduced what they call a constant velocity subliminal warp drive, and while the name might sound less exciting than Star Trek's faster-than-light warp engines, the physics represents a monumental breakthrough. For the first time, scientists have demonstrated a theoretical model for a warp drive that uses only positive energy, regular matter with ordinary gravitational properties, no exotic particles, no negative energy densities, just extremely dense ordinary matter arranged in specific configurations. The key innovation involves creating a shell of matter around the spacecraft. This shell doesn't need negative mass or exotic properties. It needs to be incredibly dense, far beyond anything we can currently create, but it's made of normal matter obeying normal physics. The researchers showed that by combining this matter shell with a carefully engineered shift vector distribution, they could achieve warp drive effects using a sophisticated blend of traditional and novel gravitational techniques. The shift vector essentially describes how the spacetime metric changes across the warp bubble, creating the contraction in front and expansion behind that enables apparent faster-than-light travel. What makes this approach revolutionary is that it satisfies all the energy conditions that physicists use to determine whether a spacetime geometry is physical. These energy conditions are mathematical requirements that ensure the spacetime doesn't violate fundamental principles. The Alcubierre drive failed these tests because negative energy violates the energy conditions. The new design passes them all. Dr. Fuchs and his team used a powerful tool they developed called Warp Factory to model and verify their design. Warp Factory is open-source software that allows researchers to simulate warp drive spacetimes, testing whether proposed geometries satisfy general relativity's equations and whether they meet the physical energy conditions. It's like a virtual wind tunnel for warp drive designs. Before Warp Factory, analysing even simple warp drive proposals could take months of hand calculations. Now, researchers can evaluate complex geometries within minutes, visualising the spacetime curvature in 2 and 3 dimensions. This capability was essential to discovering the physical warp solution. The team didn't just prove mathematically that their design could work, they created detailed visualizations showing exactly how the energy density would be distributed in the shell surrounding the spacecraft, and how momentum would flow within the warp bubble. The images are striking. The positive energy density appears in the spherical shell coloured in blues and whites, while black streamlines show the momentum flux threading through the bubble. This isn't speculation or hand-waving, it's precise physics, computed numerically, verified against general relativity's field equations. Lead author Dr. Fuchs stated clearly what this achievement means. This study changes the conversation about warp drives. By demonstrating a first-of-its-kind model, we've shown that warp drives might not be relegated to science fiction. Gianni Martir, CEO of Applied Physics, emphasized the practical trajectory. While we're not yet packing for interstellar voyages, this achievement heralds a new era of possibilities. We're continuing to make steady progress as humanity embarks on the warp age. The breakthrough eliminates the single biggest obstacle that had blocked warp drive research for 3 decades. We no longer need to discover or create exotic matter that may not exist. We don't need to violate the known laws of physics. We need to master the manipulation of ordinary matter and energy to extreme degrees, which is difficult but not impossible. This shifts warp drive research from probably impossible forever to extremely challenging but potentially achievable with sufficiently advanced technology. The implications extend beyond just one research team's success. By publishing their methods and making Warp Factory publicly available, Applied Physics has democratized warp drive research. Other scientists can now build on this foundation, testing variations, optimizing designs, searching for ways to reduce the still formidable energy requirements. This collaborative approach has already begun. The team established the Warp Fund, offering $500,000 in Phase 1 grants to researchers working on warp field mechanics. They're actively recruiting talent through their Warp Grant program, seeking creative minds to push the boundaries of what's possible. Multiple institutions worldwide have begun exploring the new design space opened by this breakthrough. We are witnessing the birth of a new scientific field, practical warp drive engineering. But before we start building starships, we need to understand exactly how these warp bubbles function and what they demand from us. The physics of warping space-time is extraordinary, even by the standards of Einstein's already mind-bending general relativity. The constant velocity subluminal warp drive creates a bubble of distorted space-time geometry around the spacecraft. Inside the bubble, space remains flat and undistorted. Clocks tick normally. Physics operates as it always has. But at the bubble's boundary, space-time curves dramatically. In front of the ship, space contracts. Behind it, space expands. These opposing distortions create a gradient that propels the bubble forward. Imagine standing on a moving walkway at an airport. You're not walking any faster than normal, but the moving surface carries you forward at an enhanced speed. The warp bubble works similarly. The spacecraft isn't accelerating through space. Space itself is flowing around the craft, carrying it along. One of the most remarkable features of warp drive travel is the absence of acceleration forces. In a conventional rocket, astronauts feel crushing g-forces during acceleration. Their bodies are pushed back into their seats as the spacecraft fights against inertia to increase velocity. But inside a warp bubble, there are no such forces. The bubble and everything in it are in free fall through curved space-time, following what physicists call a geodesic, the natural path an object takes through warped geometry. It's the same principle that allows astronauts on the International Space Station to float weightlessly. They're not in zero gravity. Earth's gravity is nearly as strong at their altitude as on the surface. They're in free fall, continuously falling around Earth. The warp bubble creates an analogous situation. The entire bubble, including the ship and crew, follows a freefall path through the distorted spacetime it has created. Acceleration happens to the bubble itself, not to objects inside it. This means, theoretically, a warp drive could accelerate to fantastic velocities, even significant fractions of light speed without the crew experiencing any g-forces whatsoever. This characteristic solves one of the major challenges of relativistic space travel. Traditional rocket propulsion, even using exotic future technologies like antimatter engines or fusion drives, would subject crews to crushing accelerations if attempting to reach significant fractions of light speed quickly. A ship accelerating at 1 g, Earth's surface gravity, would take nearly a year to reach 90% of light speed. Higher acceleration rates would shorten the time but potentially injure or kill the crew. The warp drive sidesteps this problem entirely. The comfort of the journey, however, shouldn't obscure the tremendous challenge of creating these spacetime distortions in the first place. The matter shell surrounding the spacecraft must be extraordinarily dense. We're talking about mass energy densities far exceeding anything achievable with current or near-future technology. The exact requirements depend on the bubble's size and the desired velocity, but even the most optimized designs require energy equivalent to many times the mass of large celestial bodies concentrated into relatively small volumes. Dr. Christopher Helmerich, Vice President at Celadon Solutions and co-author of the study, explained the situation candidly. Although such a design would still require a considerable amount of energy, it demonstrates that warp effects can be achieved without exotic forms of matter. These findings pave the way for future reductions in warp drive energy requirements. The research team is now focused on finding ways to reduce these energy demands. Optimizing the bubble's geometry, refining the mass distribution, identifying more efficient configurations, all of these approaches might lower the energy threshold. Some researchers are exploring whether rotating geometries or non-spherical bubble shapes could achieve similar effects with less extreme matter densities. Others are investigating whether certain materials or field configurations might enhance the spacetime curvature effect, effectively amplifying the warp field's strength. These are active areas of research, with new papers appearing regularly as scientists worldwide engage with the problem. The energy requirements, while still enormous, are no longer infinite or undefined as they were with exotic matter designs. They're just very, very large by our current technological standards. This is a crucial distinction. We know how to generate energy. We know the principles of matter manipulation, even if we can't yet achieve the required extremes. These are engineering challenges, difficult but not fundamentally impossible. In principle, a sufficiently advanced civilization could construct a warp drive using the positive energy framework. Whether humans will reach that level of advancement in decades, centuries, or millennia remains unknown. But for the first time in the history of warp drive research, we have a clear, physically valid path forward. The road is long and steep, but at least we can see it now. While warp drives manipulate spacetime's geometry to create effective faster-than-light travel, another approach involves finding shortcuts through the universe's fabric. These shortcuts are called wormholes, and while they've been a staple of science fiction for decades, they're also legitimate solutions to Einstein's field equations of general relativity. A wormhole is essentially a tunnel through spacetime connecting two distant locations. Think of spacetime as a flat sheet of paper. 2 points on the paper might be far apart when measured along the surface, but if you fold the paper so those points touch, you could punch a hole connecting them directly. The distance through the hole is far shorter than the distance across the paper's surface. Wormholes work on this principle in three-dimensional space curved through higher dimensions. A wormhole connecting Earth and a star 1,000 light-years away might have a throat, the tunnel portion, only a few kilometers long. Traveling through the wormhole would take minutes or hours instead of a millennium. The first person to seriously study traversable wormholes was physicist Kip Thorne and his colleagues in the late 1980s. They asked a specific question: could a wormhole remain open long enough and be stable enough for something to pass through? Natural wormholes, if they exist, would likely be incredibly unstable. The throat would pinch off almost instantly, severing the connection between the two mouths before anything could traverse it. Thorne and his collaborators, including Michael Morris, developed what's now called the Morris-Thorne wormhole, a theoretical construct designed to be traversable. Their analysis revealed a disappointing result. Like the Alcubierre drive, Morris-Thorne wormholes require exotic matter with negative energy density to hold them open. The exotic matter creates a repulsive gravitational effect that counteracts the wormhole's natural tendency to collapse. Without this exotic matter, the throat pinches shut. The amounts required are similar to warp drive requirements, enormous, perhaps requiring energy equivalent to Jupiter's mass converted entirely into this exotic form. For decades, this requirement seemed to doom both warp drives and wormholes to permanent theoretical status. But in 2017, physicists Ping Gao, Daniel Jaffrus, and Aaron Wall made an important discovery. They showed that wormholes could be made traversable through a process called double trace deformation, which involves quantum entanglement between the wormhole's two mouths. In this framework, the wormhole doesn't require exotic matter in the traditional sense. Instead, quantum mechanical effects, specifically the correlation between entangled quantum fields at each mouth, create the negative energy needed to stabilize the throat. This shifted wormhole physics into the realm of quantum mechanics, where negative energy densities can arise naturally from quantum fluctuations. The Casimir effect mentioned earlier demonstrates that quantum mechanics permits localized negative energy. The challenge becomes scaling these microscopic quantum effects to macroscopic wormholes large enough for spacecraft or even information to traverse. In 2022, a team including researchers from Google, Caltech, Harvard, MIT, and Fermilab achieved something remarkable. They simulated traversable wormhole dynamics on Google's Sycamore quantum processor, demonstrating that quantum systems could exhibit behaviors consistent with wormhole physics. This wasn't creating an actual wormhole in physical space-time. Rather, it was creating a quantum system whose dynamics are mathematically equivalent to a wormhole's dynamics through a correspondence called holographic duality. The experiment allowed information to enter one side of the quantum system and emerge from the other in a manner consistent with travelling through a wormhole. While this might sound like mere simulation, the holographic principle suggests something deeper. If quantum systems can perfectly reproduce wormhole dynamics, then in some sense, the quantum system is a wormhole, just expressed in a different mathematical language. This work demonstrates that the physics of traversable wormholes is real and accessible to experimental study, even if we can't yet create large-scale wormholes in ordinary space-time. Recent research published in 2024 in Classical and Quantum Gravity explored traversable wormholes in four-dimensional space-time using an Einstein-Maxwell theory with charged fermions. These fermions generate negative Casimir-like energy that stabilizes the wormhole. Importantly, the resulting wormhole configuration doesn't permit causality violations, no time travel paradoxes. It can be viewed as a pair of nearly extremal black holes with an interaction term generated by fermion field exchange. The wormhole is long, meaning the journey through it takes longer than travelling through normal space on the outside. This might seem counterintuitive for a shortcut, but it serves a crucial purpose. By making the wormhole slower than the external route, the configuration avoids closed time-like curves that would allow time travel to the past. This removes one of the major objections to traversable wormholes. The physics respects causality even while providing a tunnel through space-time. The fermion fields that stabilize this wormhole could potentially be found within the standard model of particle physics by using weak hypercharge gauge fields. The wormhole's size could be smaller than the electroweak scale, making it microscopic but theoretically consistent with known physics. The quantum physics of wormholes connects to another fascinating possibility. In 2024, researchers demonstrated wormhole teleportation protocols using quantum processors. These protocols allow information to be sent from one location to another through quantum entanglement in a way that's mathematically equivalent to sending it through a wormhole. The fidelity of this teleportation, how accurately the information is transmitted, depends on the number of qubits in the system and the strength of the coupling between the two sides. For simulating true gravitational wormholes, you need many qubits and strong coupling, approaching conditions where quantum chaos dominates. These requirements highlight the deep connection between quantum information theory, gravity, and wormhole physics. As we build larger, more sophisticated quantum computers, we'll be able to simulate increasingly realistic wormhole dynamics, potentially revealing new insights about how to create or find traversable wormholes in physical spacetime. The wormhole research landscape has expanded dramatically. Scientists are exploring wormholes in anti-de Sitter space, rotating wormholes, wormholes in modified gravity theories, and wormholes supported by exotic matter profiles like the Enasto dark matter density profile. Each variant offers different advantages and challenges. Some might be more stable, others might require less exotic matter, still others might be easier to navigate or control. The diversity of approaches reflects the field's vitality and the recognition that multiple paths might lead to practical traversable wormholes. Unlike warp drives, which require actively creating and maintaining spacetime distortions, wormholes might exist naturally in the universe. Microscopic wormholes could be constantly forming and dissolving in the quantum foam of spacetime at the Planck scale. Some theories suggest that advanced civilizations might learn to stabilize and enlarge these quantum wormholes, transforming them into macroscopic tunnels suitable for travel or communication. This would be extraordinarily difficult, requiring mastery of quantum gravity and energies approaching the Planck scale. But if natural wormholes exist, finding and using them might be easier than creating them from scratch. The connection between warp drives and wormholes runs deeper than their shared requirement for exotic matter in traditional formulations. Both represent ways to achieve effective faster-than-light travel by manipulating spacetime's topology, or geometry, rather than moving through space at superluminal speeds. Both respect general relativity's prohibition against objects exceeding light speed locally, while finding ways around the global constraint. They're different solutions to the same fundamental problem: how to traverse vast cosmic distances in reasonable times, despite the universe's light speed limit. As research continues on both fronts, insights from one area inform the other. Techniques developed for stabilizing wormholes might apply to warp drives. Energy reduction strategies for warp bubbles might translate to wormhole physics. The ultimate faster-than-light propulsion system might combine elements of both approaches, using warp drive effects to navigate normal space and wormholes to bridge truly astronomical distances. Beyond warping spacetime or creating shortcuts through it, another theoretical framework suggests that the universe might contain hidden dimensions, spatial dimensions beyond the three we experience daily. If these extra dimensions exist and we could access them, they might provide yet another route to faster-than-light travel. This idea emerges from string theory, one of the leading candidates for a unified theory of physics. String theory attempts to reconcile quantum mechanics and general relativity by proposing that the fundamental constituents of reality are not point particles, but tiny vibrating strings. These strings exist in a higher dimensional spacetime. According to the theory, the universe has 10 dimensions, 3 spatial dimensions we observe, 1 time dimension, and 6 additional spatial dimensions. These extra dimensions aren't visible to us because they're compactified, curled up so tightly that they're effectively invisible at macroscopic scales. The idea of extra dimensions isn't new. In the 1920s, physicists Theodor Kaluza and Oscar Klein discovered something astonishing. If you assume spacetime has 5 dimensions instead of 4, Einstein's equations of general relativity automatically produce Maxwell's equations of electromagnetism. Gravity in 5 dimensions looks like gravity plus electromagnetism in 4 dimensions. This hints at a deep connection between forces and geometry. The electromagnetic force, in this view, is just gravity extending into the 5th dimension. Kaluza-Klein theory originally invoked 1 extra dimension. String theory extends this to 6 extra dimensions, required to make the theory's mathematics work correctly. These extra dimensions aren't arbitrary. They're necessary for string theory to be mathematically consistent and to match the observed properties of particles and forces. The shape and size of the compactified dimensions determine what kinds of particles exist and how they interact. Different compactification geometries yield different physics. How might extra dimensions enable faster-than-light travel? Imagine a garden hose from a distance. It looks like a one-dimensional line. But an ant crawling on the hose experiences 2 dimensions: the length of the hose and the circular dimension around its circumference. From far away we can't see the circular dimension, but it's there. If we could access the hose's circular dimension, we could move in ways impossible for someone confined to the length dimension. Extra spatial dimensions in the universe work similarly. If we could enter the compactified dimensions, distances that are huge in our 3-dimensional space might be much smaller in the higher dimensional space. Traveling 1 meter through the 5th dimension might correspond to traveling thousands or millions of light years through ordinary 3-dimensional space. The challenge is accessing these dimensions. They're curled up at scales around the Planck length, approximately 10 to the negative 35 meters, far smaller than atoms, far smaller than atomic nuclei, smaller than anything we can probe with current technology. Some physicists speculate that at extremely high energies approaching the Planck energy, the compactified dimensions might become accessible or unfold. The Planck energy is approximately 1.22 times 10 to the 19 GeV, billions of times higher than energies achieved at the Large Hadron Collider. Reaching such energies would require technology far beyond our current capabilities. However, certain quantum effects might provide shortcuts. Quantum tunneling, where particles pass through energy barriers they classically shouldn't be able to cross, might allow access to extra dimensions under specific conditions. If a spacecraft could be engineered to quantum mechanically tunnel into a compactified dimension, it might traverse vast distances in our three-dimensional space by taking a shortcut through hyperspace. This remains highly speculative. We don't know if string theory is correct. We don't know if its extra dimensions exist physically or are merely mathematical conveniences. Even if they exist, accessing them might be impossible for macroscopic objects like spacecraft. Michio Kaku, a prominent theoretical physicist and popularizer of science, has written extensively about hyperspace and higher dimensions. He describes how adding dimensions can simplify apparently complex physics, much like viewing Earth from space explains weather patterns that seemed mysterious to ancient Egyptians confined to its surface. The fourth dimension and beyond might contain explanations for phenomena we find puzzling in 3 dimensions. Forces might unify in higher dimensional space. Particles might be revealed as different vibrations of strings moving through extra dimensions. The universe's fundamental structure might be far simpler and more elegant when viewed from a higher dimensional perspective. For faster-than-light travel, the key insight is that higher dimensions provide geometric shortcuts. A two-dimensional being living on a flat sheet of paper would measure the distance between 2 points along the surface, but if the paper is folded through the third dimension, those points might be brought much closer together in three-dimensional space. Similarly, three-dimensional space might be curved or folded through higher dimensions, creating shortcuts between distant locations. Some science fiction has imagined hyperspace as a parallel dimension that can be entered and navigated, where the mapping between positions in hyperspace and positions in normal space is compressed. Traveling 1 kilometer in hyperspace corresponds to thousands or millions of kilometers in normal space. While this is fictional, it captures the essential geometric idea. If reality has extra dimensions with different metric properties, different rules for measuring distance, then navigating these dimensions could provide shortcuts through the universe. The Kaluza-Klein theory's revival in the 1980s with string theory and supergravity theory brought renewed attention to higher dimensions. Physicists realized that many of the puzzles in particle physics, the proliferation of fundamental particles, the hierarchy of force strengths, the values of constants, might be explained if we're seeing only a three-dimensional slice of a higher dimensional reality. Each particle we observe might be a different vibrational mode of a string moving through 10-dimensional spacetime. Forces might be unified at high energies when the extra dimensions become relevant. In recent work, theoretical physicist Andrei Dragan and colleagues have explored how faster-than-light observers would experience spacetime. They found that at superluminal speeds, 1 + 1 spacetime, 1 spatial dimension, 1 time dimension, transforms into 1 spatial dimension and 3 time dimensions. This dimensional flip reveals a profound symmetry in physics. It suggests that faster-than-light travel might naturally involve transitioning between different dimensional configurations of spacetime. The observer wouldn't technically be moving faster than light in their local frame. Instead, they would exist in a region where spacetime's dimensional structure has been reorganized. This connects to string theory and extra dimensions because it demonstrates that the number and nature of dimensions might not be fixed. They could depend on the observer's state or velocity or energy. A spacecraft accelerating to near-light speeds or beyond might interact with spacetime dimensions in ways that fundamentally change its motion through space and time. These ideas are at the cutting edge of theoretical physics, where quantum mechanics, relativity, and higher dimensional geometry intersect. They're highly mathematical and remain unverified by experiment, but they point toward possibilities that go beyond simple warp drives or wormholes into stranger territory, where the very structure of spacetime becomes malleable. quantum mechanics introduces even more peculiar possibilities for faster-than-light effects, though with crucial limitations. Quantum entanglement, where pairs of particles maintain correlated properties regardless of distance, has sometimes been cited as enabling faster-than-light communication. When you measure one particle in an entangled pair, you instantly know something about its partner, even if that partner is on the other side of the galaxy. This correlation appears instantaneous, suggesting information travels faster than light between the particles. However, physicists have conclusively demonstrated that quantum entanglement cannot transmit information faster than light. The reason is subtle but important. When you measure an entangled particle, the outcome is random. You can't control what result you get. Therefore, you can't encode information in the measurement. The distant particle's state is correlated with yours, but because both outcomes are random and you can't force a particular result, no usable information passes between the particles. To verify the correlation, you need to compare measurements using conventional, slower-than-light communication. Only then can you confirm the entanglement. This restriction is formalized in the no-communication theorem of quantum mechanics. It states that quantum entanglement, despite its non-local character, cannot be used to send messages faster than light. Any attempt to force one particle into a specific state breaks the entanglement, leaving the other particle completely unaffected. The correlation exists only for measurements performed without trying to control the outcome. Despite this limitation, quantum mechanics does exhibit faster-than-light correlations in a limited sense. When entangled particles are measured, their states become correlated instantaneously across any distance. This spooky action at a distance, as Einstein called it, has been verified experimentally many times. Photons separated by hundreds of kilometers show correlations that violate classical physics expectations. Recent experiments at the Large Hadron Collider observed quantum entanglement in top quarks, extending these observations to the highest energies yet achieved. The correlations are real and instantaneous. They just can't be used to transmit information or violate causality. Some researchers have explored whether quantum effects might enable other forms of faster-than-light phenomena. Quantum tunneling allows particles to cross energy barriers they classically couldn't overcome. In some interpretations, the particle appears on the other side of the barrier instantaneously, suggesting faster-than-light traversal. However, careful analysis shows that no information travels faster than light during tunneling. The process respects relativistic causality. Another quantum phenomenon, the Casimir effect, creates measurable forces from virtual particle fluctuations in the quantum vacuum. These forces arise from electromagnetic fields in the vacuum, having different energy densities in different regions. The Casimir effect has been verified experimentally and is now being explored as a potential source of the negative energy needed for warp drives and wormholes. If quantum vacuum fluctuations can be manipulated to produce controlled negative energy densities, they might enable macroscopic spacetime engineering. Quantum field theory predicts that the vacuum isn't empty but filled with quantum fluctuations, virtual particles constantly appearing and disappearing. These fluctuations have measurable effects on atomic energy levels, magnetic moments of particles, and the Casimir force. They represent a real, physical aspect of the vacuum. Some physicists propose that by manipulating these vacuum fluctuations, perhaps through carefully designed electromagnetic fields or nanoscale structures, we could generate regions of negative energy density. The amounts would be tiny, but if we could amplify them or concentrate them effectively, they might serve as the exotic matter needed for warp drives or wormholes. This is highly speculative, and current experiments have only produced negative energy at microscopic scales in carefully controlled laboratory conditions. Scaling to spacecraft-sized applications would require breakthroughs we can barely imagine. But it connects quantum mechanics to the macroscopic goal of faster-than-light travel in potentially fruitful ways. The intersection of quantum mechanics and general relativity remains one of physics' great unsolved problems. A complete theory of quantum gravity would describe how spacetime behaves at the smallest scales, where both quantum effects and gravitational effects are important. Such a theory might reveal new possibilities for manipulating spacetime that neither quantum mechanics nor general relativity alone could predict. String theory is one attempt at quantum gravity, proposing that gravitational and quantum effects are unified through strings vibrating in higher dimensional spacetime. Loop quantum gravity is another approach, suggesting that spacetime itself is quantized, made of discrete units at the Planck scale. Neither theory is complete or confirmed experimentally, but both hint that the fabric of reality at the deepest level is stranger and more malleable than everyday experience suggests. If we could master quantum gravity, we might gain capabilities that seem like magic by today's standards. Creating wormholes, warping space-time, accessing extra dimensions, all of these might become routine engineering problems once we understand how to manipulate space-time's quantum structure. Even with breakthroughs in theoretical understanding, practical faster-than-light travel faces a monumental challenge: energy. Every proposed method requires enormous amounts of energy, far beyond what current or near-future technology can provide. The applied physics warp drive design, while avoiding exotic negative energy, still demands massive quantities of ordinary energy configured into extraordinarily dense matter shells. The exact requirements depend on the bubble's size and desired velocity, but even optimistic estimates require energy equivalent to large celestial bodies. Let's put this in perspective. The Sun's total mass energy, calculated using Einstein's famous equation E equals mc squared, is approximately 1.8 times 10 to the 47 joules. That's the energy you'd get if you could convert the Sun entirely into energy. The original Alcubierre drive required negative energy equivalent to Jupiter's mass, which is about 1.9 times 10 to the 45 joules of positive energy equivalent. The newer designs have reduced requirements somewhat, but we're still talking about energy scales comparable to large planets or small stars. To put this in more familiar terms, the total energy consumption of all human civilization in a year is approximately 6 times 10 to the 20 joules. The energy needed for even the most efficient warp drive designs is billions of times greater than humanity's total annual energy production. We would need to capture and harness the output of entire stars for years or decades to accumulate the necessary energy. This places warp drives and similar technologies firmly in the realm of Kardashev Type II civilizations capable of harnessing the total energy output of their star. Humanity currently ranks at approximately 0.7 on the Kardashev scale, still dependent on planetary energy sources. Reaching Type II status would require fundamental advances in energy generation, storage, and manipulation. We'd need technologies like Dyson spheres or equivalent megastructures to capture stellar output. We'd need energy storage methods far beyond chemical batteries or even antimatter containment. We'd need propulsion systems and energy conversion methods that approach theoretical efficiency limits. Some researchers have proposed ways to reduce warp drive energy requirements. Optimizing the bubble's shape, using toroidal or elliptical geometries instead of spheres, can lower the energy density needed at each point. Harold White's work at NASA suggested that a carefully designed warp bubble geometry might reduce energy requirements by several orders of magnitude. Instead of requiring the Sun's mass energy, perhaps we'd only need Jupiter's mass energy, or even less. Every order of magnitude reduction brings the goal closer to theoretical feasibility. Advanced propulsion concepts like antimatter engines could theoretically produce enormous energy densities. Matter. Antimatter annihilation converts mass to energy with 100% efficiency, unlike nuclear reactions which convert only a tiny fraction of mass to energy. A kilogram of antimatter annihilating with a kilogram of matter releases about 1.8 times 10 to the 17 joules of energy, roughly the yield of a 43 megaton nuclear bomb. For warp drive applications, we'd need tons or thousands of tons of antimatter. Currently, humanity produces antimatter in microscopic quantities measured in nanograms, and it costs approximately $62.5 trillion per gram. Scaling up antimatter production by 15 orders of magnitude, while reducing costs by similar factors, would require revolutionary advances in particle physics and engineering. Other exotic energy sources have been proposed. Zero-point energy extraction from the quantum vacuum, if possible, could provide nearly limitless power. The vacuum fluctuations that create the Casimir effect represent an energy reservoir pervading all of space. If we could tap this reservoir efficiently, we might solve the energy problem. However, extracting usable energy from the vacuum without violating thermodynamics remains unproven and controversial. Some physicists argue it's fundamentally impossible, others believe we simply don't know how to do it yet. Fusion energy, while less exotic than antimatter or vacuum energy, represents a more near-term possibility. Controlled fusion reactors, when perfected, could provide energy densities orders of magnitude higher than chemical or fission reactions. A future civilization with mature fusion technology, perhaps using advanced fuels like helium-3 or proton-boron reactions, might generate enough power to begin experimenting with small-scale warp effects. This wouldn't enable interstellar travel immediately, but it could allow laboratory demonstrations of spacetime manipulation, validating the theoretical principles and pointing toward eventual practical applications. The energy problem connects directly to mass manipulation. The applied physics warp drive requires a shell of extremely dense matter surrounding the spacecraft. Creating such density means compressing matter far beyond normal states. The densest naturally occurring matter we know is found in neutron star cores, where atomic nuclei are crushed together into a solid mass of neutrons. Neutron star material has a density around 4 × 10 to the 17 kilograms per cubic meter. A teaspoon would weigh billions of tons on Earth. Even neutron star density might not be sufficient for optimal warp bubble generation. We might need to approach or exceed this density in carefully shaped configurations around the spacecraft. Handling such matter would require technologies we can barely conceive. How do you contain material that dense? How do you shape it into precise geometries? How do you prevent it from collapsing into a black hole under its own gravity? These questions have no current answers but point toward required capabilities. Advanced civilizations would need mastery over matter at the most fundamental levels, able to manipulate it into any configuration regardless of normal material constraints. Some physicists have suggested that we might not need to actually create these extreme densities using ordinary matter. Perhaps we could use intense electromagnetic or gravitational fields to curve space-time directly, without relying on matter as an intermediary. General relativity tells us that energy in any form creates space-time curvature. Electromagnetic fields carry energy. Sufficiently intense fields might generate the necessary curvature for warp effects. The field intensities required would be stupendous, but they might be more achievable than assembling neutron star density matter shells. Research in this direction explores what are called field-driven warp metrics, where electric or magnetic fields or exotic field configurations create the space-time distortions. The mathematics is complex, and the energy requirements remain enormous, but this approach might offer alternative pathways to the same goal. Ultimately, the energy problem might be solvable not through generating more power, but through discovering more efficient ways to manipulate space-time. Every reduction in the required energy density or total energy makes the goal more achievable. If future theoretical breakthroughs reveal ways to create warp effects with less energy, perhaps by exploiting quantum properties or using resonant space-time geometries, the timeline to practical implementation shortens dramatically. This is why research continues despite the daunting energy scales. We're learning how to do warp physics. Once we understand it fully, the energy requirements might drop to merely difficult rather than nearly impossible levels. The publication of applied physics breakthrough has sparked intense interest worldwide. Gianni Maltia, founder and CEO of Applied Physics, described the current environment as a space race brewing. He explained to media that recent unprecedented breakthroughs in physics and propulsion have launched world powers into what he calls a 21st century space race to build the world's first working warp drive. This isn't hyperbole. Multiple nations and private organizations have begun investing in warp drive research, recognizing its potential strategic and economic value. The technology that enables interstellar travel would revolutionize civilization, offering access to resources, real estate, and knowledge beyond anything available in Earth's solar system. Military applications are obvious as well. A warp-capable spacecraft would dominate any conventional vessel, reaching targets before defenses could react, positioning forces anywhere in a star system at will. Warp technology could reshape geopolitical dynamics as profoundly as nuclear weapons or spaceflight itself. Applied physics has positioned itself at the forefront of this emerging race. Their Advanced Propulsion Laboratory represents the cutting edge of warp drive research, bringing together physicists, engineers, and computational scientists from around the globe. The lab has published multiple peer-reviewed papers on warp drive physics, each advancing the field incrementally. Their Warp Factory tool has become the standard for evaluating warp drive designs, used by researchers at universities and research institutes worldwide. By making this tool open source and publicly available, Applied Physics has accelerated the field's development, while establishing themselves as leaders. The Warp Fund and Warp Grant program actively recruit talent into this new discipline. Researchers who might otherwise have worked on more conventional physics problems are being drawn to warp drive research by the combination of scientific challenge and potential real-world impact. The fund has already distributed $500,000 in Phase 1 grants, with more funding planned for Phase 2 and beyond. Grant recipients work on various aspects of warp field mechanics, from fundamental theoretical questions to numerical simulation techniques to potential experimental tests. Other organizations and nations are ramping up their own efforts. While specific programs remain largely classified or unpublicized, patterns in published research, conference proceedings, and personnel movements suggest significant activity in China, Russia, and European Union nations, as well as continued work in the United States. Private aerospace companies with interests in advanced propulsion are also paying attention. Though most remain focused on near-term technologies like ion drives and nuclear thermal propulsion, some are beginning to allocate resources toward more exotic concepts, positioning themselves to capitalize if breakthroughs occur. The space race metaphor is apt in another way. Like the original space race between the United States and Soviet Union, competition in warp drive development could accelerate progress beyond what peaceful cooperation alone might achieve. Nations and organizations racing to be first will invest heavily, accept higher risks, and push the boundaries of what's possible. This competitive environment, while potentially dangerous, might be exactly what's needed to transform warp drives from theoretical curiosities to engineering projects. However, unlike chemical rockets or even nuclear weapons, warp drives cannot be built with current technology plus incremental improvements. The energy and matter manipulation requirements are too extreme. The race isn't to build a warp drive now. It's to establish the scientific and engineering foundations that will enable construction decades or centuries hence. This makes it a different kind of competition, less about immediate production and more about long-term strategic positioning. Researchers involved in warp drive physics emphasize that we're still in the basic research phase. Applied physics breakthrough eliminated one major obstacle, the exotic matter requirement, but enormous challenges remain. We need better understanding of how to reduce energy requirements. We need developments in materials science, energy generation, and spacetime manipulation that don't yet exist even in nascent form. We need experimental tests of warp field effects, starting at microscopic scales and gradually working toward macroscopic demonstrations. Each step will take years or decades. Some scientists are exploring whether warp drive effects might already be detectable in nature or in sensitive instruments. If natural processes occasionally create tiny warp bubbles, even at quantum scales, we might be able to detect them. Gravitational wave detectors like LIGO, designed to sense ripples in spacetime from colliding black holes and neutron stars, might also detect signatures from warp bubbles forming or collapsing. In 2024, physicists published a paper describing the gravitational wave signature that would result from a collapsing warp bubble. For Star Trek fans, this is essentially a warp core breach. The collapse would send ripples through spacetime at characteristic frequencies. If we tuned our gravitational wave detectors to these frequencies, we might detect warp drives being operated by other civilizations, even at great distances. This prospect is objectively awesome, in the words of researcher Katie MacDonald. It suggests we might discover evidence of alien warp-capable species through their accidents or experiments, opening a window into the technological capabilities of extraterrestrial civilizations. The implications of successful warp drive development extend far beyond engineering. Humanity becoming a warp-capable species would mark a transition as profound as the invention of agriculture, writing, or industrial machinery. We would no longer be confined to Earth or even the solar system. The galaxy would become accessible, not in generations-long voyages, but in journeys measured in years or even months. We could establish outposts around other stars, investigate potentially habitable worlds up close, access resources from multiple star systems, and begin the process of becoming a true interstellar civilization. The philosophical and societal changes would be equally dramatic. Humanity has always been limited by geography and resources. Space travel has been the domain of a tiny elite due to the enormous expense and danger. Warp drives would eventually democratize interstellar travel, allowing ordinary people to visit other worlds, to see alien sunsets, to walk on the surfaces of distant planets. The expansion of human experience beyond one world would reshape our understanding of our place in the universe. But alongside these exciting possibilities come serious concerns. Warp-capable vehicles would be powerful, potentially dangerous tools. A warp drive could serve as a devastating weapon. A spacecraft entering or exiting warp drive might release enormous energy. If directed at a planet, this could cause catastrophic damage. The technology would need strict international oversight and control. Treaties governing warp drive development and deployment would become necessary, much like nuclear non-proliferation agreements. The question of who controls this technology and who has access to it would create new geopolitical tensions. In interviews with applied physics researchers, they acknowledge these concerns but emphasize that we're still far from having to address them practically. The technology is in its infancy. By the time warp drives become feasible to build, humanity will hopefully have developed the wisdom and institutions to manage them responsibly. The alternative, restricting research to prevent misuse, would likely fail and would certainly slow progress that could benefit all of humanity. One of the more intriguing aspects of warp drive research involves potential detection of warp bubbles through their gravitational signatures. When a warp bubble forms, moves, or collapses, it creates disturbances in spacetime that propagate as gravitational waves. These waves carry energy and information about their source, just as electromagnetic waves carry information about stars, galaxies, or other astronomical objects. Gravitational wave astronomy is still a young field. LIGO and similar detectors have been operating for less than a decade in their advanced configurations, detecting mergers of black holes and neutron stars. The instruments are exquisitely sensitive, able to detect space-time distortions smaller than the width of a proton. As the technology improves and new detectors come online, the sensitivity will increase further. This opens the possibility of detecting gravitational signatures from warp drives, operated by advanced civilizations. The physics of collapsing warp bubbles predicts specific gravitational wave frequencies and patterns. These signatures would be distinct from natural sources like merging compact objects or cosmic strings. If we observed such a signal, it would provide strong evidence that someone, somewhere, was manipulating spacetime with technology. The paper published in 2024 detailed what these signatures should look like, giving observational astronomers a template to search for in existing and future data. Finding evidence of alien warp drives would be momentous. It would confirm we're not alone in the universe and that at least one other species has achieved this technological milestone. It would provide data about how warp drives actually work in practice, potentially accelerating our own development. We could study the frequency, duration, and energy of the signals to infer details about the drive's operation. This represents a new form of SETI, the search for extraterrestrial intelligence, based not on radio signals but on gravitational wave techno-signatures. Of course, detecting such signals requires luck and patience. Space is vast, and warp-capable civilizations might be rare. The signals would be weak, attenuated by distance. We'd need the event to occur relatively nearby, cosmically speaking, and we'd need to be observing at the right time with instruments pointed in the right direction. But the beauty of gravitational wave detectors is that they observe large fractions of the sky continuously. Unlike optical telescopes that must be aimed at specific targets, gravitational wave instruments are sensitive to signals from any direction. This increases the chances of serendipitous detection. As our network of detectors expands, with facilities planned for India, Japan, and possibly space-based detectors, our sensitivity to these signatures will improve. Even if we never detect an alien warp drive, the search itself drives innovation in detector technology and data analysis. The techniques developed to identify warp bubble signatures might prove useful for finding other exotic phenomena or improving our understanding of known sources. The connection between gravitational wave astronomy and warp drive research exemplifies how basic science and applied engineering reinforce each other. Warp drive theory predicts gravitational signatures, motivating improved detectors. Better detectors enable new discoveries about the universe, potentially including evidence of technological civilizations. Those discoveries inform our understanding of what's possible, feeding back into warp drive development. This virtuous cycle accelerates progress in multiple fields simultaneously. Researchers in both areas recognize the synergy, and are beginning to collaborate more closely. Gravitational wave physicists are consulting with warp drive theorists about what signals to look for. Warp drive researchers are learning from gravitational wave astronomy about how to model and compute spacetime dynamics. These cross-disciplinary connections strengthen both fields and increase the likelihood of breakthroughs. If humanity does successfully develop warp drives, what would practical interstellar travel look like? Let's consider a journey to Alpha Centauri, the nearest star system to Earth at 437 light-years away. With current technology, even our fastest spacecraft would require tens of thousands of years for this trip. Chemical rockets are too slow. Ion drives, while more efficient, still produce modest accelerations. Even theoretical fusion rockets or antimatter drives, operating continuously at high thrust, would take decades to reach Alpha Centauri and decades more to slow down and return. Warp drive changes the calculation entirely. If we could create a warp bubble moving at significant fractions of light speed, the journey time drops dramatically. At 10% of light speed, the trip would take about 44 years each way. At 50% of light speed, less than 9 years. At 90% of light speed, just under 5 years. These are still long voyages, but they're within a human lifetime. A crew could launch as young adults and arrive in their middle age. Round trips become conceivable. But subliminal warp drives, while revolutionary, don't achieve the truly dramatic speed-ups that science fiction has led us to imagine. For that, we'd need to somehow exceed light speed. The applied physics design operates at constant subliminal velocities, staying below the light barrier. This respects causality and avoids the paradoxes associated with faster-than-light travel. However, it limits the maximum speed to just under light speed. To travel across the galaxy's 100,000 light-year diameter would still require over 100,000 years, even at 99.9% light speed. For truly rapid interstellar exploration, we'd need either wormholes to create shortcuts or breakthroughs that allow genuinely superluminal warp bubbles without causality violations. Some theoretical work suggests this might be possible in certain spacetime configurations or by invoking exotic physics beyond general relativity. But for now, these remain speculative. Even subliminal warp drives would transform human civilization in ways we're only beginning to imagine. Access to nearby stars within single lifetime journeys would enable settlement of exoplanets, exploitation of interstellar resources, and direct investigation of other solar systems. We could send scientific missions to study planets around Alpha Centauri, Barnard's star, Sirius, or dozens of other nearby stars currently beyond our reach. Each of these systems represents a completely unknown domain. What planets orbit these stars? Do any harbour life, even microbial? What resources exist in their asteroid belts and moons? What can we learn about stellar evolution and planetary formation by studying these systems up close? The answers would fill libraries and fuel scientific discovery for generations. We could establish outposts or colonies on habitable worlds, creating backup locations for humanity that would survive local catastrophes. This concept, known as planetary insurance, acknowledges that keeping all of humanity on one world is dangerous. Asteroid impacts, pandemics, climate disasters, nuclear war, or other existential threats could devastate Earth. Having populations established around multiple stars would ensure humanity's survival, even if Earth became uninhabitable. This redundancy would transform our species from vulnerable to resilient, from fragile to anti-fragile. The psychological impact of becoming an interstellar species would be equally profound. Humans would no longer be confined to one fragile planet or even one star system. We would have taken the first real step toward becoming a starfaring civilization. The philosophical implications would permeate every aspect of culture. Our myths, our religions, our sense of identity would all shift to accommodate this new reality. We would no longer be Earthlings, but something greater, citizens of the galaxy, explorers of the cosmos. Consider what this means for human potential. Every child would grow up knowing that the stars are reachable, that humanity's domain extends beyond Earth's atmosphere. Career opportunities would expand to include asteroid mining in the Tau Ceti system, terraforming projects on worlds orbiting Epsilon Eridani, or xenobiology research on potentially life-bearing planets. The frontier would be genuine and limitless. Human ambition would have a natural outlet in exploration and settlement that could absorb our species' energy for millions of years. The engineering challenges of operating a warp-drive spacecraft are formidable beyond the drive itself. Life support systems would need to function reliably for years or decades without resupply or repair from Earth. Every component would require redundancy. Air recycling systems would need backup systems and backup backups. Water purification couldn't fail for even a day without risking the crew. Food production, whether through hydroponics, preserved stores, or some combination, would need to sustain the crew for the entire journey plus contingency reserves in case of delays. Radiation shielding presents one of the most serious technical challenges. In interstellar space, far from the Sun's protective magnetosphere, spacecraft are exposed to galactic cosmic rays, high-energy particles that can damage DNA, electronics, and spacecraft structures. Current spacecraft use minimal shielding due to mass constraints, accepting elevated radiation exposure for short-duration missions. But for journeys lasting years or decades, radiation protection becomes critical. Heavy metals like lead or tungsten could provide shielding, but they're dense and expensive to accelerate. Water or hydrocarbon materials offer lighter alternatives, serving dual purposes as both radiation shields and consumable resources. Some designs propose surrounding the crew habitat with tanks of water or waste, using them as makeshift radiation barriers. More advanced concepts involve electromagnetic deflection systems that create artificial magnetic fields around the spacecraft, deflecting charged particles the way Earth's magnetosphere does. These active shielding systems would require substantial power, but could provide better protection with less mass than passive shields. Navigation systems would track position across light years with unprecedented precision. In the solar system, we navigate using a combination of radio tracking from Earth, star positions, and inertial guidance systems. For interstellar travel, Earth-based tracking becomes impossible due to distance and signal lag. The spacecraft must navigate autonomously, using star positions, pulsar timing, and careful dead reckoning based on its trajectory and the warp drive's performance. Pulsars, rapidly rotating neutron stars that emit regular radio pulses, act as natural cosmic lighthouses. Their pulse periods are extraordinarily stable, making them ideal reference points for navigation. By measuring the arrival times of pulses from multiple known pulsars, a spacecraft can triangulate its position in space to high precision. This technique has been demonstrated in principle and would form the backbone of interstellar navigation systems. However, the warp bubble itself might distort or block pulsar signals, requiring the spacecraft to occasionally drop out of warp to take navigation fixes. These interruptions would add time to the journey, but ensure the crew knows exactly where they are. Communication with Earth would face delays of years at light speed. A message sent from Alpha Centauri would take over 4 years to reach Earth, and the reply would take another 4 years to return. This means crews must be prepared to make critical decisions without consulting mission control. They would need complete authority to respond to emergencies, alter mission plans, or even abort and return home if circumstances demanded it. This autonomy requirement has profound implications for crew selection and training. Mission commanders would need judgment and experience comparable to naval captains of the age of exploration, when ships might spend years away from home with no contact with their governments. The crew would need technical skills to maintain and repair the spacecraft, using only the resources aboard. Every system would need to be designed for maintainability. Modular components that can be swapped out or repaired with basic tools, spare parts for critical systems, comprehensive documentation and training so crew members can troubleshoot problems they've never encountered before. In essence, the spacecraft would need to be a self-sufficient mobile workshop, capable of manufacturing or repairing almost anything it might need. 3-dimensional printing and advanced manufacturing systems would be essential. Rather than carrying spare parts for every possible failure, the ship would carry raw materials and fabrication systems capable of producing parts on demand. Metal printers, polymer extruders, electronic assembly systems, all would allow the crew to manufacture replacement components as needed. This technology is already being developed for the International Space Station and future Mars missions, but interstellar missions would require far more sophisticated and capable systems. The crew themselves represent another critical resource that must be sustained over the journey. Physical health requires exercise facilities to prevent muscle atrophy and bone density loss in the microgravity or low-gravity environments. Medical facilities would need to handle everything from routine care to emergency surgery, with the crew members themselves trained in medical procedures since specialised doctors might not be available. Mental health support becomes equally important on journeys lasting years in confined spaces. Psychological screening would identify candidates best suited for long-duration isolation. Training would prepare crew members for the emotional challenges. The spacecraft would need recreational facilities, private spaces, communication systems for staying in touch with Earth despite the lag, and possibly psychological support AI systems to provide counselling. The spacecraft would need to be large enough to carry supplies, equipment and crew for the duration of the mission, plus substantial margins for contingencies. Unlike science fiction, where crews are routinely put into suspended animation or cryogenic sleep, we have no such technology and no clear path to developing it. The crew would be awake and active for the entire voyage, living their lives aboard the ship for years. This means providing not just survival resources but quality of life, food that's nutritious and palatable, not just nutrition bars and recycled water, entertainment and communication systems to maintain morale, work that's meaningful and engaging. The spacecraft would essentially be a small settlement in motion, more comparable to a village or town than a traditional vehicle. Think of it as a flying community of specialists, each contributing their expertise to keep the mission functioning. Crew size calculations involve difficult trade-offs. Smaller crews minimize life support demands, reduce interpersonal conflicts, and require less volume and mass, but they lack redundancy in skills and labor. If the one engineer who understands the power systems becomes incapacitated, the mission could fail. Larger crews provide redundancy, diverse expertise, and better social dynamics. Humans are social creatures. We don't thrive in groups of 3 or 4 for years on end. We need community, varied interactions, different personalities and perspectives. But every additional crew member increases mass, life support requirements, living space, food, water, and air. Some mission planners suggest crews of around 12 to 20 people as a sweet spot, large enough for social stability and skill redundancy, small enough to keep the spacecraft mass manageable. Others argue for crews exceeding 100 to create a genuine community with specialists in every discipline. The optimal number remains debated and would vary depending on mission duration, destination, and spacecraft capabilities. Power generation during the voyage presents another substantial engineering challenge that's often underestimated. Once the warp drive is engaged, and the bubble is cruising at constant velocity, the drive itself might require minimal power to maintain that state. The applied physics model operates at constant velocity, suggesting that once established, the warp bubble becomes self-sustaining, or at least requires far less energy than creating it initially required. But all the ship's other systems would still demand power continuously. Life support, navigation, communications, lighting, computers, medical equipment, manufacturing systems, and crew comfort all consume energy. The power demands would be substantial, kilowatts at minimum, possibly megawatts for larger ships with extensive facilities. Solar panels become useless once you're far from any star. In interstellar space, the sun appears as just another bright star, providing negligible energy. Solar power might work in the departure star system or arrival system, but for the years or decades of transit through deep space, another solution is needed. Nuclear fission reactors could provide steady power for decades using uranium or plutonium fuel. Current nuclear submarine reactors operate for 30 years or more without refueling, demonstrating the technology's maturity. Scaling up to spacecraft applications introduces challenges. Reactors are heavy. They produce waste heat that must be radiated away, and they require shielding to protect the crew from radiation. But the fundamental technology exists and works. Nuclear fission has powered spacecraft before, from the Soviet Rorsat satellites to NASA's proposed nuclear thermal rockets. An interstellar spacecraft might use multiple reactors for redundancy, with one operating while others remain in reserve. If antimatter becomes available as fuel for the warp drive, a portion of it could be diverted for power generation. Matter-antimatter annihilation produces tremendous energy, far more than fission or fusion. A few grams of antimatter could power the spacecraft for the entire mission. The challenge is containing and controlling antimatter safely. It annihilates instantly on contact with normal matter, requiring magnetic containment systems similar to those used in experimental fusion reactors. Any failure of containment means catastrophic explosion. The technology is theoretically possible but far beyond current capabilities. Advanced fusion reactors represent another option, potentially cleaner and safer than fission with comparable energy density. Deuterium-tritium fusion produces helium and neutrons, releasing energy without the long-lived radioactive waste of fission. The fuel could be derived from water in the ship's life support system, making it renewable over long durations. Fusion power remains elusive on Earth despite decades of research, but an interstellar spacecraft would have different constraints. The reactor doesn't need to produce net energy for sale to a power grid. It just needs to sustain itself and power the ship's systems. Lower efficiency might be acceptable if the system is reliable and maintainable. Some researchers believe that fusion power will be practical for spacecraft before it becomes economically viable for terrestrial power generation, due to different performance requirements and constraints. These power systems would need to operate continuously for years or decades in the vacuum of space, exposed to cosmic radiation, with no possibility of resupply or external repair. Reliability becomes paramount. Every component would be tested exhaustively. Redundancy would be built in at every level. Maintenance schedules would ensure components are inspected and replaced before they fail. The engineering philosophy would resemble that of nuclear submarines: conservative design, proven technology, extensive testing, and rigorous maintenance protocols. The economic implications of warp drive technology, once it becomes practical, would reshape global and eventually galactic civilization. Currently, space activities generate hundreds of billions of dollars annually, but they're limited to near-Earth operations, satellite communications, GPS, remote sensing, and occasional robotic exploration of the solar system. Interstellar capabilities would expand this economic space by factors of millions or billions. Consider asteroid mining, currently a speculative venture targeting near-Earth asteroids. The resource base expands dramatically when you can access asteroids in other star systems. A single metallic asteroid might contain trillions of dollars worth of platinum group metals, rare earths, and other valuable elements. Multiply that by thousands of accessible asteroids across dozens of star systems, and you're looking at resource availability that dwarfs Earth's entire crust. The economic value could be comparable to or exceed all of terrestrial GDP, creating wealth on scales difficult to comprehend. Real estate represents another economic dimension. Habitable or terraformable planets around other stars would be worth enormous sums. A planet with breathable atmosphere, liquid water, and benign biosphere could support billions of people and generate economic activity for centuries. Even marginal worlds requiring environmental engineering would have value. The first entities or nations to claim and develop these worlds would gain economic and strategic advantages. This creates incentives for rapid expansion once warp drives become available, potentially leading to a land rush not seen since the colonization of the Americas. Scientific and technological benefits would flow back to Earth and other settled worlds. Studying alien ecosystems, even if only microbial, would revolutionize biology and medicine. Novel biochemistries might produce pharmaceuticals or industrial materials impossible to create with terrestrial chemistry. Geological and astronomical data from other systems would refine our understanding of planetary formation, stellar evolution, and cosmology. Each new world studied adds to humanity's knowledge base, driving innovation and discovery. The strategic military value of warp drive technology cannot be ignored, however uncomfortable the topic might be. Any nation or organization possessing warp-capable spacecraft would dominate those without. Warp ships could position forces anywhere in a star system within hours or days, striking before defenses could react, escaping before retaliation could arrive. They could control access to resource-rich asteroids or strategic locations. They could deny adversaries access to space beyond their home systems. This power imbalance would create intense pressure for warp drive proliferation, where every major nation or power bloc would seek to acquire the technology to avoid being left defenseless. It echoes the nuclear arms race, but with potentially greater consequences since warp drives enable not just weapons delivery, but expansion and resource acquisition that could shift the balance of power permanently. International governance of warp drive technology would become essential, but extraordinarily difficult. Who decides which nations or entities can develop or deploy warp drives? How do we prevent military applications while allowing civilian exploration and commerce? What authority enforces these rules across interstellar distances where Earth's governments have no practical jurisdiction? These questions have no easy answers. Historical attempts at arms control and technology governance have met with mixed success at best. The Outer Space Treaty of 1967 prohibits national sovereignty claims on celestial bodies and bans weapons of mass destruction in space, but it was negotiated when spaceflight was limited and interstellar travel impossible. A new framework would be needed for the warp drive era, one that balances exploration, development, safety, equity, and security. Creating such a framework while warp drives remain theoretical might be the best approach, establishing principles and institutions before vested interests and power dynamics calcify around the technology. Navigation in interstellar space is fundamentally different from navigation in the solar system, presenting challenges that require entirely new approaches and technologies. There are no GPS satellites, no convenient planetary reference points, no radio beacons. Navigation would rely primarily on star positions, pulsar timing signals, and dead reckoning based on the ship's acceleration and trajectory. Each method has strengths and limitations. Optical navigation using star positions is the most straightforward approach. The spacecraft would image the surrounding star field using telescopes and compare it to databases of known star positions and distances. By measuring the angular positions of multiple stars and accounting for parallax effects from the spacecraft's motion, navigation systems could calculate position to within a few astronomical units under ideal conditions. This accuracy degrades with distance from Earth, but it provides a reliable backup method that requires no external infrastructure. Pulsar navigation offers superior precision for deep space positioning. Pulsars emit regular radio pulses with extraordinarily stable periods, some maintaining timing accuracy better than atomic clocks over decades. By measuring the arrival times of pulses from multiple known pulsars, a spacecraft can triangulate its position in three-dimensional space, with precision approaching tens of kilometers, remarkable accuracy across interstellar distances. NASA has demonstrated pulsar navigation technology with the NISA instrument on the International Space Station, proving the concept works in practice. The warp drive itself could complicate navigation, because the bubble's geometry might affect how light and radio signals from external sources appear to the crew. Spacetime curvature bends light paths, potentially distorting the positions of stars and shifting the arrival times of pulsar signals. The navigation system would need to account for these relativistic effects, calculating corrections based on the bubble's geometry and the spacecraft's velocity through warped space. This requires sophisticated computational models and real-time measurements of the warp field's characteristics. Dead reckoning, calculating position based on known starting point, velocity and elapsed time, provides continuous position updates between fixes from external sources. Inertial navigation systems measuring the spacecraft's acceleration in all three axes can integrate this data over time to track position. However, small errors accumulate, causing position uncertainty to grow with time. Periodic corrections using star positions or pulsar timing would bound this error growth. The combination of these methods, optical star sighting, pulsar timing, and inertial dead reckoning, would provide robust navigation capability even if one or two methods become unavailable temporarily. Redundancy and cross-checking between independent measurements would ensure position accuracy throughout the voyage. Testing warp drive technology will follow a graduated approach starting at the smallest scales and incrementally working toward full-scale interstellar capability. The progression from theory to practice will likely span decades or even centuries, with each phase building on the previous one's successes and lessons. Phase 1 would involve laboratory demonstrations of microscopic warp effects. Using the most advanced energy concentration techniques available, perhaps ultra-high-powered lasers or particle accelerators, researchers would attempt to create tiny spacetime distortions at femtometer or nanometer scales. These wouldn't move anything visible or achieve practical velocities, but they would prove the fundamental principles work. Detecting such minute warp fields would require extraordinarily sensitive instruments, possibly including atomic clocks that could measure the subtle time dilation effects or gravitational wave detectors capable of sensing the tiny spacetime ripples. Success at this phase would confirm that the theoretical models correspond to physical reality and guide optimization of warp field geometries and energy configurations. Phase 2 would scale up to macroscopic demonstrations affecting objects visible to the naked eye. Imagine a laboratory apparatus that creates a warp bubble around a small sphere, perhaps a few centimeters in diameter, and accelerates it along a track at velocities exceeding what conventional forces could achieve. The apparatus might use superconducting electromagnets or contained antimatter reactions to generate the necessary energy densities. The sphere wouldn't travel at relativistic speeds yet. The energy requirements would be too extreme, but it might reach velocities demonstrably greater than could be explained by conventional acceleration. This phase would develop the engineering technologies needed for warp field control, power delivery, field stability, and bubble containment. It would also validate computational models against experimental measurements, refining our understanding of warp drive physics. Phase 3 might involve small unmanned spacecraft, achieving warp velocities sufficient to make journeys within the solar system faster than conventional propulsion allows. A probe travelling from Earth to Mars under warp drive could complete the journey in days or weeks instead of months. This would demonstrate operational warp technology in realistic space environments, testing how the drive performs in vacuum, how it handles navigation and course corrections, and how it interacts with natural gravitational fields from planets and the Sun. These missions would be robotic initially, removing the risk to human life while proving the technology's safety and reliability. Dozens or hundreds of unmanned warp drive test flights might precede the first crewed mission, just as robotic spacecraft explored the Moon before Apollo astronauts landed there. Phase 4 would see the first crewed test flights, likely within the solar system initially. Astronauts would travel to Mars, the asteroid belt, or perhaps Jupiter's moons under warp drive, validating that human crews can operate safely inside warp bubbles and that life support systems function correctly under warp field conditions. These missions would be relatively short, lasting months rather than years, allowing crews to return quickly if problems arise. Success at this phase would prove that crewed interstellar missions are feasible. Phase 5, finally, would be the first interstellar missions to nearby stars. These would likely target the closest systems, Alpha Centauri, Barnard's Star, or Wolf 359. Mission durations would depend on the warp drive's maximum velocity, ranging from several years for the closest targets to a decade or more for systems farther out. The first crewed interstellar voyages would be historic moments comparable to the first moon landing or the first circumnavigation of Earth. They would mark humanity's transition from a single planet species to an interstellar civilization. Each phase could take years or decades to complete. Phase 1 laboratory demonstrations might occur within 20 to 50 years if funding and scientific progress continue at optimistic rates. Phase 2 macroscopic demonstrations could follow 10 to 30 years later as technologies mature. Phase 3 unmanned test flights might happen 50 to 100 years from now, and Phase 4 crewed test flights perhaps 100 to 150 years from now. Phase 5 interstellar missions could begin late in the 22nd or early in the 23rd century. These timelines are highly speculative and depend on sustained investment, breakthrough discoveries, and absence of major setbacks. Pessimistic timelines could add decades or centuries to each phase. Optimistic scenarios might compress the schedule if revolutionary discoveries accelerate progress. The unpredictability is inherent in transformative technologies. No one in 1900 could have accurately predicted that humans would land on the Moon within 70 years, or that powered flight would go from impossible to routine within decades. Similarly, we cannot confidently predict exactly when warp drives will transition from theory to practice, but we can say with increasing confidence that the transition will happen eventually, that the physics allows it, and that humanity is beginning the long journey toward that goal. The human factors of long-duration interstellar travel have been studied in the context of generation ships and sleeper ships, but warp drives present new considerations. The crew would know they're isolated from Earth by years of communication lag. Help cannot arrive in an emergency. They must solve problems themselves using only the resources aboard. This psychological burden requires careful crew selection and training. The crew would need technical skills to maintain and repair the spacecraft, but also emotional resilience and interpersonal compatibility to endure years in close quarters. Analog missions on Earth, such as long-duration simulations in isolated environments, provide some preparation, but the reality of being light years from home would test even the best-trained crews. Some researchers propose small crews of a dozen or fewer, minimizing life support demands and interpersonal friction. Others argue for larger crews to provide redundancy, diverse skills, and better social dynamics. The optimal crew size remains debated and would likely vary depending on mission objectives and spacecraft capabilities. Despite all these challenges, the prospect of visiting other stars within human lifetimes would inspire efforts comparable to the Apollo program or even greater. The first crewed warp drive mission to another star would be one of humanity's defining moments, comparable to the first moon landing, the first circumnavigation of Earth, or the first controlled nuclear reaction. Billions would watch as the spacecraft departed, gathered around screens showing the historic moment when humanity took its first intentional step beyond the solar system. The journey itself would capture public imagination for years, as updates arrived periodically describing the crew's experiences, the spacecraft's performance, and the approaching destination. And years later, when signals finally arrived reporting successful arrival at another star system, the celebration would be global and profound. The data returned from even a single interstellar mission would transform our understanding of planetary systems, stellar evolution, and the prevalence of life in the universe. Remote sensing through telescopes, no matter how powerful, can only reveal so much. We can detect exoplanets, measure their sizes and orbits, analyze their atmospheric compositions spectroscopically. But we cannot examine their surfaces closely, cannot study their geology directly, cannot search for biosignatures with the sensitivity that close-range instruments provide. Direct observation trumps remote sensing every time. A warp-capable spacecraft could orbit an exoplanet for months, mapping it completely, landing probes on its surface, perhaps even sending crew members down in landers if the environment permits. The level of detail and understanding gained from such close examination would dwarf anything achievable through even the most sophisticated telescope observations from Earth. Consider what we might learn from visiting a potentially habitable world around another star. We could determine whether life has emerged there independently. If it has, we could study an entirely separate instance of biology, revealing whether life on Earth represents universal principles or just one possible pathway among many. Are DNA and RNA the only possible information storage molecules for life? Does all life require liquid water, or can biochemistry operate in other solvents? Do all organisms use similar metabolic pathways, or has alien life discovered fundamentally different ways to harness energy? These questions have profound implications for biology, chemistry, and our understanding of life's nature. They can only be answered by studying life wherever we find it, which means travelling to other worlds and examining them directly. Even worlds without life would offer immense scientific value. Pristine planetary systems untouched by human activity could reveal how planets form and evolve without the complications of industrial civilization. We could study geological processes on worlds with different compositions, gravities, and thermal histories. We could examine atmospheres unlike Earth's, learning how atmospheric chemistry and dynamics operate under different conditions. Each new world would be a natural laboratory, offering insights impossible to gain by studying Earth alone. The knowledge acquired would fill entire libraries, inspiring new theories, technologies, and industries. The economic value of interstellar access is harder to quantify, but potentially enormous beyond anything in human experience. Asteroids in other systems might contain rare elements or materials unavailable or scarce on Earth. Platinum group metals, essential for catalytic converters, fuel cells, and chemical processing, exist in low concentrations in Earth's crust because they sank into the core during planetary formation. But metallic asteroids could contain these elements in much higher abundances. A single, large metallic asteroid might hold more platinum, iridium, and similar metals than have been mined throughout human history. The economic potential extends far beyond raw materials. Exoplanets might offer habitable environments worth trillions of dollars in real estate value alone. A planet with breathable atmosphere, liquid water oceans, temperate climate, and no hostile life forms would be priceless. It could support human settlement without requiring extensive terraforming or life support systems. Millions or billions of people could eventually migrate there, establishing a new branch of human civilization. Even less hospitable worlds would have value if they could be terraformed over centuries using techniques like atmospheric engineering, climate modification, or ecological seeding. The first organizations or nations to claim and develop these worlds would gain economic and strategic advantages that could persist for millennia. Unique ecosystems with biochemistries different from Earth's might produce pharmaceuticals, industrial materials, or biotechnology products impossible to create using terrestrial biology. Imagine a world where life evolved different metabolic pathways, producing novel enzymes that catalyze reactions we can only achieve through expensive industrial processes, or organisms that synthesize materials with properties we cannot replicate in our factories. The biotechnology and material science applications could be revolutionary, driving economic growth for generations. Geological and astronomical data from other systems would refine our understanding of planetary formation, stellar evolution, and cosmology at the most fundamental levels. How do different stellar metallicities affect planetary system architecture? What geological processes operate on high-gravity super-Earths? How do ice giant atmospheres evolve over billions of years? Each new world studied adds data points that constrain and improve our theoretical models. This knowledge has practical applications. Better understanding of planetary processes helps us predict volcanic eruptions, earthquakes, and climate changes on Earth. Better understanding of stellar evolution helps us forecast the Sun's long-term behavior and prepare for its eventual expansion into a red giant. The strategic military value of warp drive technology cannot be ignored, however uncomfortable the topic might be for those who prefer to focus on scientific and exploratory applications. Any nation or organization possessing warp-capable spacecraft would dominate those without such capabilities. Warp ships could position military forces anywhere in a star system within hours or days, striking targets before defenses could react, projecting power across interplanetary distances that would take conventional vessels months or years to traverse. They could control access to resource-rich asteroids or strategic locations like Lagrange points. They could deny adversaries access to space beyond their home planets, establishing blockades that would be nearly impossible to break without equivalent technology. This asymmetric capability would create intense pressure for warp drive proliferation among nations and power blocks. Every major nation would recognize that falling behind in this technology could mean permanent strategic disadvantage or even conquest. The race to develop warp drives wouldn't just be about exploration or prestige, it would be about survival and sovereignty in an era when control of near space no longer guarantees security. If one nation achieved warp capability while others did not, the imbalance could be catastrophic. The warp-capable nation could position forces in orbit above any point on Earth within hours, neutralize satellites, intercept missiles during boost phase, or deliver devastating attacks from space before ground-based defenses could respond. This capability would make current military balances obsolete almost overnight. The historical parallel to nuclear weapons is obvious but imperfect. Nuclear weapons created a strategic balance through mutually assured destruction. Using them guaranteed retaliation that would destroy the attacker. Warp drives don't necessarily create such a balance. A nation with warp ships could strike first, neutralize an adversary's space capabilities, and establish control before retaliation became possible. This makes warp technology potentially more destabilizing than nuclear weapons in some scenarios. It also creates powerful incentives for international cooperation and arms control agreements before the technology matures. Treaties governing warp drive development, deployment, and use would become essential for maintaining global security. But negotiating such treaties would be extraordinarily difficult. How do you verify compliance when warp drive research could occur in secret facilities? How do you enforce restrictions when the technology itself enables nations to escape oversight by moving operations to remote locations in the solar system or beyond? The challenges of governance extend beyond military applications to questions of resource access, territorial claims, and human rights. Who owns an asteroid belt around another star? Does the nation that reaches it first gain ownership? Does a private company that establishes mining operations there have exclusive rights? What happens when multiple entities claim the same resources? How do we prevent a scramble for interstellar territory that replicates the worst aspects of colonial history, where native populations were displaced or exterminated, and resources extracted without regard for environmental consequences? These aren't hypothetical questions. They're practical governance challenges that would emerge immediately once warp drives become operational. Current space law, primarily the Outer Space Treaty of 1967, provides some framework but was negotiated when interstellar travel was impossible and even lunar bases were speculative. The treaty prohibits national sovereignty claims on celestial bodies, and bans weapons of mass destruction in space, but it doesn't address scenarios like corporate asteroid mining, interstellar colonization, or encounters with alien life. A new comprehensive framework would be needed for the warp drive era, one that balances exploration, development, safety, equity, security, and long-term sustainability. This framework should ideally be established before warp drives become practical, while nations can negotiate from relatively equal positions without the distortions created by some possessing the technology and others lacking it. But history suggests that governance structures often lag behind technological developments, emerging only after problems become acute. The international community may need to learn hard lessons before agreeing on effective frameworks for managing warp drive technology and interstellar expansion. Creating governance structures now while warp drives remain theoretical might be humanity's best chance to avoid catastrophic conflicts or injustices later. This requires foresight and cooperation that nations have rarely demonstrated, but the stakes justify extraordinary efforts. The transition from a single planet species confined to Earth to a multi-system civilization distributed across many stars represents one of the most profound transformations in human history. How we manage that transition will determine whether humanity's expansion into the galaxy brings prosperity and enlightenment or conflict and tragedy. The choice is ours to make, but we must make it wisely and soon, before the technology's development outpaces our ability to control its consequences. As we look toward the future of warp drive development, timeline predictions vary widely. Optimists suggest that with sufficient funding and effort, we might see laboratory demonstrations of microscopic warp effects within a few decades. These wouldn't move anything macroscopic or achieve practical speeds, but they would prove the concept and guide further development. Midterm projections, perhaps 50 to 100 years out, might see the first experimental spacecraft achieving warp velocities sufficient to make journeys within the solar system faster than conventional propulsion allows. Testing a warp drive between Earth and Mars, for example, could validate the technology while remaining relatively close to home. This would be analogous to early aviation, where the first flights covered short distances at low speeds before eventually enabling transatlantic and then global travel. Full-scale interstellar-capable warp drives might emerge in a century or two, assuming continued scientific progress and societal investment. This timeline depends on numerous factors: advances in energy generation, materials science, computational simulation, and fundamental physics. It also depends on sustained political and economic support for what would be an enormously expensive, long-term research program with uncertain payoff dates. History shows that major technological developments often proceed faster than pessimists predict and slower than optimists hope. Flight from the Wright brothers to commercial jet aviation took about 50 years. Spaceflight from early rockets to moon landings took roughly 40 years, but both benefited from intense competition and generous funding driven by military and political incentives. Warp drive development might follow a similar trajectory if nations perceive strategic value in the technology, or it might languish with only modest research funding, extending the timeline to centuries. Some researchers believe that the real breakthroughs will come not from engineering but from new physics. If we discover a deeper theory of quantum gravity, or if experiments reveal unexpected properties of spacetime, the landscape could shift dramatically. Phenomena we don't currently understand might provide shortcuts to warp drive capabilities. This is speculative, but not unprecedented. Quantum mechanics revolutionized technology in ways its early developers never anticipated, giving us lasers, transistors, nuclear power, and countless other innovations. A similar revolution in our understanding of spacetime could enable warp drives and more. Until then, we work with the physics we know, pushing its boundaries, testing its limits, exploring every possible avenue toward practical faster-than-light travel. The work continues in universities and research institutes around the world. Theorists refine their models, computational scientists develop more sophisticated simulations, engineers begin thinking about what materials and energy sources might eventually serve warp drive construction. The philosophical implications of warp drive technology deserve careful consideration, as they touch on fundamental questions about humanity's place in the cosmos and our relationship with the universe. For centuries, the speed of light has been the ultimate barrier. defining the limits of human expansion and experience. It has constrained not just our physical reach, but also our ambitions and imagination. The galaxy has always existed for us as an abstract concept, a collection of distant lights beyond any realistic hope of visitation. Our myths, religions, and philosophies have developed within the context of cosmic isolation. We are Earth dwellers, products of this specific planet's evolution, shaped by its environment and constrained by its confines. The idea that we might someday visit other worlds has been fantasy, not serious planning. Breaking this barrier, even through the clever loophole of warping spacetime rather than truly exceeding light speed, would fundamentally reshape our relationship with the cosmos in ways both obvious and subtle. We would transition from being bound to our solar system, a tiny bubble of space around one average star, to being truly cosmic citizens with the galaxy as our domain. This would affect religion, philosophy, art, culture, and every aspect of human thought and expression in profound ways that we can barely anticipate. Religious traditions developed on Earth often place humanity at the center of cosmic significance, created by divine powers for specific purposes. How do these narratives adapt when we discover that the universe contains countless worlds, many potentially harboring life, stretching across distances so vast that our entire civilization occupies an insignificant fraction of one galaxy among hundreds of billions? Some religious thinkers have already begun grappling with these questions, recognizing that the discovery of extraterrestrial life, whether microbial or intelligent, would require theological adaptation. But actually traveling to other stars, establishing human presence across multiple systems, encountering alien biospheres, these would force much deeper reconsideration of fundamental religious premises. Are humans unique in the cosmos, or just one intelligent species among many? Is Earth special, or merely one habitable world among countless others? These aren't just academic questions. They touch on issues of meaning, purpose, and identity that have sustained billions of people for millennia. The answers we discover as we explore the galaxy will reshape religious and philosophical thought for generations. Philosophers have long debated questions of consciousness, free will, meaning, and ethics within the context of earthbound human existence. But what happens to these debates when humans are spread across multiple star systems, living in radically different environments, potentially diverging culturally and even biologically over thousands of years of separation? Would a human raised on a high-gravity super-Earth, spending their entire life in an environment 3 times Earth's surface gravity, develop the same philosophical perspectives as someone born on a low-gravity moon? Would colonists living underground on an airless world, dependent on technology for every breath and every drop of water, see existence differently than those on Earth-like planets with breathable atmospheres and abundant water? The question of maintaining human unity and shared identity across light years of separation becomes increasingly important the more we consider the implications. Even with warp drives making travel possible, journeys between stars would still take years, and communication would face light-speed delays, creating conversational pauses measured in years for the most distant systems. Communities separated by such distances would inevitably develop independently, creating distinct cultures, languages, values, and potentially even divergent evolutionary paths if genetic isolation persists for thousands of generations. How do we preserve any sense of shared humanity when different branches of our species become strangers to each other? This problem has historical precedents in the divergence of cultures on Earth due to geographic isolation, but the scales are incomparably larger in space. Polynesian settlers spreading across the Pacific Islands over centuries developed distinct cultures despite common ancestry. European colonization of the Americas created societies that diverged from their parent cultures in just a few generations. Imagine these processes operating across light years and millennia. The humans living around Alpha Centauri in the year 5000 might be as different from Earth humans as we are from Neanderthals, not through extinction and replacement, but through simple evolutionary divergence enhanced by different selective pressures on different worlds. Should we try to prevent this divergence, maintaining genetic and cultural homogeneity across our expanding civilization? That would require unprecedented coordination and control, essentially managing human evolution across star systems. Or should we accept divergence as natural and beneficial, recognizing that diversity strengthens species and cultures alike? Different answers to these questions would lead to radically different futures. A humanity that maintains unity might develop into a galactic civilization with shared values, knowledge, and identity spanning millions of worlds. A humanity that diverges might eventually become multiple distinct species, some perhaps unrecognizable as having common ancestry with Earth humans. Neither future is inherently better or worse, but they're profoundly different, and the choice, to the extent we have one, would be among the most important our species ever makes. The search for extraterrestrial intelligence takes on new urgency and different character in a future where humans possess warp drives. Currently, SETI focuses on detecting radio signals from technological civilizations, assuming that such civilizations would eventually develop radio technology, and that some might broadcast signals intentionally or unintentionally into space. This search operates over interstellar distances with light speed limitations. Any signal detected would be years, decades, or centuries old by the time we received it. Communication would be correspondingly delayed, making real-time conversation impossible. With warp drives, the dynamics change completely. We could respond to detected signals by actually visiting their source within reasonable timeframes. A signal from a civilization 100 light-years away might take a century to reach us, but our warp-driven response mission could arrive at their world within a few years of launch. This creates interesting scenarios. If we're on the verge of becoming a warp-capable species, perhaps other civilizations have already achieved this milestone. The galaxy might be far more accessible to advanced beings than we've assumed, populated by travelers from many worlds exploring, trading, or colonizing across interstellar distances. The Fermi paradox, the apparent contradiction between high estimates for the probability of extraterrestrial civilizations and the lack of contact with them, might be partially explained by the difficulty of achieving warp drive technology. If very few civilizations surmount this barrier, remaining confined to their home systems, contact would be correspondingly rare even if intelligent life is common. We might be surrounded by civilizations that can broadcast radio signals but cannot travel between stars, essentially isolated on cosmic islands. Alternatively, if warp drives are achievable by many species given sufficient time and technological development, then the lack of contact suggests either that we're among the first to reach this point, which seems statistically unlikely in a galaxy billions of years old, or that advanced civilizations deliberately avoid contact with younger species for reasons we can only speculate about. Perhaps there exists a galactic protocol of non-interference, where mature civilizations watch emerging ones from a distance, but don't make contact until the newcomers achieve certain technological or cultural thresholds. Perhaps warp-capable species recognize that premature contact could be devastating to less advanced civilizations, causing cultural shock, dependency, or conflict. Or perhaps advanced civilizations simply don't find pre-warp species interesting enough to bother contacting, focusing their attention on peers at similar technological levels. As we develop our own warp capability, we might gain insight into which explanation is correct. If we start detecting gravitational wave signatures from other civilizations' warp drives, we'll know that the technology is achievable by multiple species, and that we're not alone in the cosmos. If we travel to other stars and find ruins or artifacts from long-dead civilizations but no living representatives, we might conclude that technological species frequently achieve interstellar capability but then fail to sustain it over long timescales. If we encounter active alien civilizations that greet us or attempt contact when we arrive in their systems, we'll face the most profound challenge in human history: establishing communication, understanding their nature and intentions, and forging relationships that could determine our species' fate. The responsibility that comes with warp drive technology cannot be overstated. We would have the power to reach and potentially influence pristine worlds throughout our region of the galaxy. We could discover planets with their own ecosystems, even if only microbial life, and face decisions about whether to preserve those ecosystems intact or modify them for human use. We could encounter alien species and choose whether to contact them peacefully, avoid them entirely, or, worst case, exploit or harm them. Every choice would have consequences extending far into the future, affecting not just humanity but potentially numerous other species and entire planetary biospheres. The ethical frameworks we develop for interstellar exploration and colonization will be crucial in determining whether our expansion into the galaxy proves beneficial or catastrophic. History offers sobering lessons about what happens when technologically advanced cultures encounter less advanced ones. The European colonization of the Americas, Africa and Asia brought tremendous suffering to indigenous populations through disease, displacement, enslavement, and cultural destruction. These weren't inevitable consequences of contact. They resulted from specific choices made by colonizers who valued wealth and power over justice and human dignity. As we contemplate human expansion into the galaxy, we must ask ourselves hard questions. Will we repeat the mistakes of terrestrial colonization on an interstellar scale? Will we treat alien worlds and their potential inhabitants with respect and caution? Or will we exploit them ruthlessly for resources and territory? Will we establish principles of universal rights that extend beyond humanity to include all sentient beings we encounter? Or will we prioritize human interests exclusively? These are not idle questions, but practical considerations that would face any civilization beginning to explore and settle other star systems. The answers we choose will define what kind of civilization we become. We could be responsible stewards of the galaxy, preserving and protecting the diverse life and environments we encounter, while expanding carefully and ethically. Or we could become cosmic conquerors, taking what we want without regard for consequences, leaving destruction in our wake. The choice is ours, but it must be made thoughtfully and soon, because once warp drives become operational, we'll be committed to whatever path we've chosen. The galaxy deserves better from us than mere repetition of terrestrial history's worst chapters writ large across the stars. As this journey through the science of faster-than-light travel comes to a close, several themes emerge with crystalline clarity. First, the dream of travelling faster than light is no longer purely science fiction, relegated to the pages of novels or the imaginations of screenwriters. Real physics, published in peer-reviewed journals by respected scientists at major institutions, demonstrates paths that could lead to practical warp drives. These paths are difficult, requiring technologies far beyond our current capabilities and energy resources that dwarf anything humanity can currently harness. But they're not impossible. They don't violate the fundamental laws of physics. They don't require us to discover new forces or overturn centuries of confirmed experimental results. They require us to become more advanced, more capable, more masterful at manipulating matter and energy. That's difficult but achievable given sufficient time and effort. Second, progress is accelerating in ways that would have seemed impossible just a few years ago. The 2024 breakthrough eliminating the exotic matter requirement represents a genuine paradigm shift in warp drive research. We've moved from "this probably can't be done" to "this is extremely hard but potentially achievable with sufficiently advanced technology." That psychological shift matters enormously. It transforms warp drive research from a fringe pursuit, attractive only to dreamers and eccentrics, into a legitimate field attracting serious researchers from major institutions. Graduate students can now pursue warp drive physics as a career path, without being dismissed as unrealistic. Funding agencies take proposals seriously that would have been rejected out of hand a decade ago. The field has reached a tipping point where progress feeds on itself, attracting more talent, generating more insights, and accelerating toward practical applications. Third, international competition is driving investment and effort in ways that pure scientific curiosity alone might not achieve. The emerging space race in warp drive technology could accelerate progress significantly, channeling resources and talent toward the goal at unprecedented scales. But it also carries risks of misuse, military applications, and destabilizing conflicts. Managing this technology's development will require wisdom, foresight, and international cooperation at levels humanity has rarely achieved. The alternative, allowing warp drives to develop without governance frameworks or ethical guidelines, could lead to catastrophic consequences that would overshadow any benefits the technology provides. Fourth, the challenges ahead are genuinely multidisciplinary, requiring advances across virtually every field of science and engineering. Success will require breakthroughs in theoretical physics to better understand spacetime's quantum structure, engineering advances to manipulate matter at extreme densities and energies, material science to create structures capable of withstanding the stresses involved in warp field generation, energy generation technologies orders of magnitude beyond current capabilities, computational simulation to model and optimize warp drive designs, navigation and control systems for spacecraft operating in warped spacetime, life support for crews on journeys lasting years or decades, The list goes on. No single breakthrough will suffice. We need progress on many fronts simultaneously, which makes warp drive development a grand challenge worthy of civilization's best efforts and brightest minds. Fifth, the timeline remains uncertain but finite, and that uncertainty itself tells us something important. Whether it's decades, centuries, or longer, humanity appears to be on a path toward achieving warp drive technology, assuming we don't destroy ourselves or abandon the effort. The question isn't whether, but when. This makes decisions we make today about governance, ethics, and priorities consequential in ways that extend far into the future. The frameworks we establish now will shape how warp drives are developed and deployed. The values we embed in our institutions will determine whether interstellar expansion brings prosperity or conflict. We're not just building a technology, we're defining what humanity will become as we spread across the stars. Finally, and perhaps most importantly, the implications of success would be transformative beyond measure, in ways both practical and philosophical. Becoming a warp-capable species would alter human destiny, opening the galaxy to exploration and settlement, answering ancient questions about our place in the cosmos, and launching humanity on a journey that could last millions of years. We would transform from a vulnerable single-planet species at risk of extinction, from local catastrophes, into a distributed multi-system civilization resilient enough to survive almost any disaster. We would encounter wonders that would expand our understanding of life, physics, and reality itself. We would face challenges that would test our wisdom, ethics, and adaptability, and we would become something greater than we are today, not just technologically but spiritually and intellectually, shaped by the vast experience of exploring and inhabiting diverse worlds across vast distances. For those of us alive today, we likely won't see operational interstellar warp drives, but we are witnessing the foundational research that will make them possible. We're part of the generation that transitioned warp drives from fantasy to physics. That's a remarkable position to occupy in human history. The scientists and engineers working on these problems today are building the foundations for a starfaring civilization that our descendants will inhabit. Their work matters, not just for the practical goal of faster-than-light travel, but for what it represents: humanity's refusal to accept arbitrary limits, our determination to reach beyond the comfortable and familiar, our drive to explore and understand the universe that gave birth to us. The speed of light is not the final barrier, it's simply the next one we'll overcome. Right now, the universe appears vast beyond comprehension, with distances so great that crossing them seems impossible. But throughout history, impossible journeys have become routine. Crossing the Pacific Ocean once seemed as fantastic as crossing interstellar space seems today. Yet humans accomplished it with wooden ships and primitive navigation. Flying to the moon was fantasy until we did it. Impossible is often just difficult in disguise. The path to the stars is long and steep, filled with challenges that will test our ingenuity, our patience, and our resolve. But the path exists. We can see it now, traced in equations and simulations, mapped in theoretical papers and research programs. We know the direction to go. We're taking the first steps, and someday, perhaps sooner than we think, humanity will cross the light-speed barrier not by breaking the laws of physics, but by mastering them, by using reality's own geometry to create shortcuts through space-time. We will build ships that warp space itself, that slip between the stars as easily as we now cross continents. And when that day comes, when the first warp drive activates and carries humans to another star system in a single lifetime, we'll look back at this era as the beginning. The time when we realized the universe was not as closed to us as we feared. The time when we learned that the stars are not unreachable. The time when we discovered how to travel 10 times faster than light. If this journey through the cutting edge of physics has inspired you, hit that like button and subscribe to Space Reports for more explorations of the universe's deepest mysteries and humanity's boldest dreams. The future is being built right now, one equation at a time, one simulation at a time, one breakthrough at a time, and you're here to witness it. Thank you for watching.